Okay, welcome to our next installment about rational functions. The last video was all about determining some features of rational functions, namely vertical asymptotes, holes of a rational function, and the end behavior or its horizontal asymptote. Now this video is going to be about how do those show up on a graph, and how do we use that information to sketch a rational functions graph. So we'll look at a couple of different examples. That's mainly what this is going to be, is me going through lots of examples of graphing rational functions. Let me go ahead and give you the steps to graph a rational function. Learning objective is to graph a rational function, including vertical asymptotes, any holes, horizontal asymptotes, and the x and y intercepts. So these are all general things you want to show on the graph of any function if they exist. And so, sometimes sometimes our rational functions will have x-intercepts, sometimes they'll have y-intercepts, sometimes they won't. Sometimes they'll have vertical asymptotes. If we have that, then we want to graph it. All right, so remember, rational functions are going to be functions where you have a polynomial on top divided by another polynomial. So polynomial over polynomial. So when we want to graph it, we do the same things we did in the last exercise, which were finding all of the holes, vertical asymptotes, and the horizontal asymptote. But in addition to that, we're going to want to find the x and y intercepts as well. These will help us sketch the graph because they're going to give us definite points to plot on our graph of the rational function. The x-intercepts are going to be zeros. So the x-intercepts are zeros of the numerator. And so they're zeros that are not asymptotes or holes. Occasionally zeros of the numerator give you a hole or an or it's still an asymptote. And in the case of that, it's not an x-intercept. It's not going to be equal to 0 there. But if it's a 0 of the top and not of the bottom, so if it's ever going to be 0 divided by something that's not 0, well, the result is 0, so those are going to be x-intercepts. They're going to be places where it crosses the x-axis. The y-intercept is easier to find. That's just the result of evaluating the function at x equals 0. So you just plug 0 in and see what shakes out. All of the x's go away, and it's going to be the constant term on the top over the constant term on the bottom. And then the last thing, once you've got the x-intercepts, once you've got the y-intercept, if there is one, the holes, the vertical asymptotes, and the horizontal asymptotes, we're going to do this thing I call sign analysis, where we want to figure out what is the sign, positive or negative, which is, is the answer positive or a negative answer, to the function if we're close to the vertical asymptote. So just to the left of the vertical asymptote, what's the sign going to be? And just to the right of the vertical asymptote, what's the sign going to be? This is actually going to help us sketch the graph, because then we know if it's positive, it's going to be blowing up, and if it's negative, it's going to be zooming down near that vertical asymptote. Okay? Because it could be doing one or the other, either going to positive infinity or negative infinity. And really, we just need to know the sign. Is it a positive answer or a negative answer? And that's enough to know if it's going up or if it's going down. And I'll do an example where we do sign analysis a little bit later. With all that information, once you've got the holes, the vertical asymptotes, the horizontal asymptote, the x and y intercepts, and you've determined, what's happening close to each of those asymptotes, then you can start plotting. So you can plot each asymptote as a dashed line, and each hole that's as an open circle. You can plot the x and y intercepts, and then you can use that sign analysis to determine, are you going up to infinity or are you going down to negative infinity when you're going close to that to those asymptotes. And that should be sufficient to be able to sketch the graph. Okay. All right, so let's go ahead and get started with an example. So the parent function for a rational function is the one that looks like 1 over x. So f of x equals 1 over x is a simple function. We're going to go ahead and find the asymptotes see if there's any holes, find its x-intercepts, y-intercept, and so forth. So we know x equals 0 is a vertical asymptote since it's a 0 of the denominator, q, but it's not a 0 of the top. There's no numbers that make the top 0. It's 1. It's always 1. So we're going to sketch the vertical asymptote x equals 0. So over here on my graph, I'm going to draw in x equals 0. Okay, there's my vertical asymptote. Now there are no holes on this for this graph because nothing makes the top 0 and the bottom 0. There's no canceling factors. So, all right, we've got 1, we've got 2 done. We're going to find the horizontal asymptote next. Well, the denominator wins the race. We have 1, which is staying 1 the whole time, over x, which if we're looking at end behavior, x is getting bigger and bigger, 1 is staying the same, 1 over x is going to go to 0. So this is my horizontal asymptote. It's the same as the end behavior. So I'm going to sketch that in, y equals 0. So there's the horizontal asymptote. All right, so I drew those as dashed lines because they're not actually on our graph. They're just guides for graphing the horizontal, or graphing the rational function 1 over x. So don't draw them in as complete lines because they're not actually on our graph. Okay, there are no x-intercepts for 1 over x because 1, the numerator, is never 0. So there's no zeros of p. So what we're going to do is we're going to, since there's no x-intercepts, we have none to sketch, so we're going to just move on to the next thing. There are no y-intercepts either. Why are there no y-intercepts? Well, if we try to plug 0 in, f of 0, we get 1 over 0. That's not allowed, right? 0 is outside our domain. That's our vertical asymptote. So it doesn't cross the it doesn't hit the y-axis anymore, or anywhere. So we have no y-intercepts. So we can skip that. All right, so then the next part, which is the sign analysis, which is the thing that I said we're going to talk more about. So sign analysis is asking, what is the result, the sign, just the sign of the result? I don't actually need to know the answer. I just want to know what's the sign, positive or negative, near our vertical asymptote. So we're going to look just to the left of 0. So we're going to look at f of negative 0.1, for example. That's just to the left of 0. To the left of 0. Smaller than 0. And we want to know the sign. Well, the sign of the top is positive because 1 is positive. The sign of the bottom is negative. Why is the bottom negative? Well, it's 1 over negative 0.1. Right? Negative 0.1 is a negative number, so we have negative on the bottom. So the result of this, a positive number divided by a negative number, is a negative number as our answer. And so what that tells us is that it's going down to negative infinity to the left of 0. So we can sketch that in. We know to the left of 0, I'm going to use actually just a different color entirely to do this. To the left of 0, it's going down to negative infinity. So we know that because of this sign analysis. And then we can do the same thing to the right of 0. So if we were to look at f of 0.1, well, we have a positive on top and a positive on bottom, and the result of a positive divided by a positive is a positive number. And so we know it's going up to infinity on the other side, on the right side of 0. So just on the right side of 0, it's going to positive infinity because the result is a positive answer. On the left side of 0, it's going down to negative infinity because the result is a negative answer. Okay? So this is what is telling us the sign of the answer close to that vertical asymptote. That's telling us which way to go, up or down. We could plot some other points if we want to. We know the result of 1, f of 1 is equal to 1 over 1, which is 1. So I'm going to just plot that guy right there. There's 1, and there's negative 1, f of negative 1, equals -1. That's right there. So we can sketch those guys, and it's going to look something like that. It's going to zoom in towards that horizontal asymptote from above on the right. So it's going to zoom in towards that horizontal asymptote from above. And on the left, it's going to zoom in towards that horizontal asymptote from the bottom, from below, because it's negative to the left of, for negative x's. It's negative over there. It's positive on the right, negative on the left. Okay? All right, and just to double check my work, I'm going to go ahead and plug this into Desmos and see if I get the same answer. Are we good? There we go. Okay, there's 1 over x. We can see that vertical asymptote x equals 0. Go ahead and make it a dashed asymptote. And we can see the horizontal asymptote at y equals 0. And as we go towards 0 from the right, it's going up to infinity. As we go towards 0 from the left, it's going down to negative infinity. We had those key points, you know, -1, and 1, 1. We could sketch those in because those were easy to evaluate. We don't really need any other points on our graph. We can sketch the rest of it, you know, from just the asymptotes. Okay? It doesn't cross the x-axis at all. It doesn't cross the y-axis. There's no x or y intercepts for 1 over x. Okay, let's do another one. Okay, this is a special case, special kind of rational function you might have. Our function's x squared minus 4 over x plus 2. So our first step is we want to factor the numerator and the denominator. And that's generally what you want to do because you want to figure out what makes the top 0 and what makes the bottom 0, and factoring is the easiest way. So if we factor the numerator and the denominator, we're going to get x plus 2 times x minus 2 over x plus 2. And what happens after you cancel your common factors, x plus 2's cancel, you're left with a linear function x minus 2, where x can't be -2. There's a little hole in a linear function. And so this is actually very easy to sketch. There's no vertical asymptotes because there's no zeros of the denominator that are also not zeros of the numerator. There's no horizontal asymptote. The degree of the top is more than the degree of the bottom. And there's a hole. There's a hole when x is equal to -2 and when at the point -2, -4. Now how did I find that -4 part? Well, that's when you plug -2 in here. So I'm going to plug -2 into the reduced version, and I get -4 as my answer. So that's where my hole is. So we'll go ahead and plot this. It's just the line x minus 2, and x can't be -2. So let's plot that. I know that my y-intercept is at -2. My slope is 1. So I'm going to do my best with this pen. Oh, that's pretty good. That's not bad. Okay. And then we have a hole at -2, -4. So I'm going to do a little open circle there. And then we're going to go down and to the left. It's as best as I can do. So this is the line x minus 2, and there's a hole plucked out from it. So it's a linear function in disguise, and just so that you see it on Desmos as well, and I always encourage you when you have these problems to graph them with a graphing calculator to check your work. Let's go ahead and take a look. It's going to give us a line. See our linear function x squared minus 4 over x plus 2. And we can see, now it doesn't look like there's a hole. I said there was a hole at -2, -4, but if you were to zoom in and try to evaluate it, I'm going to switch to presenter mode so it's easier to see. If you evaluate it right at -2, there is no function there. It's undefined. And so you'd represent that with a little open circle, just the way that they have it here. Okay, with that little open circle. There we go. So you can actually plot it like this if you really want to make it stand out. Circle, and there we go. You can see that there's that open circle at -2, -4. Okay, so that's a linear function. Okay, next example. This is a little bit more. There's a little bit more going on here. Our function is x squared minus 1 over x squared minus 5x plus 4. So we're going to factor the top and the bottom like we do to find the zeros. Factoring the numerator, you get x plus 1, x minus 1. Factoring the denominator, let me go back up there. Factoring the denominator, we get x minus 4 and x minus 1. And so you should see from that these are going to cancel, and our function simplifies to x plus 1 over x minus 4. And again, I write x can't be 1 to keep track in my head, to remember that there's going to be a hole in this function. There's going to be a little hole plucked out when x is 1. So from this we can read the vertical asymptote. There's a vertical asymptote at x equals 4. So that's 0 of that. We have a horizontal asymptote when y is equal to y is equal to 1. And that's because that's our ratio of leading terms is just 1, right? X squared over x squared is 1. Our hole is at 1, negative 2/3. And how do we find that negative 2/3 again? Well, we plug it in. We plug 1 in. So that's going to give us 1 plus 1 over 1 minus 4. And what that is equal to is 2 over negative 3. And so that's our y value for the hole. The x value for the hole is that x, the x that you're not allowed to plug in, that common 0 at the top and the bottom. So we have a hole, we've got a vertical asymptote, and we've got a horizontal asymptote. We have an x-intercept. There is an x-intercept on this function. The x-intercept is x equals negative 1, because that's a 0 of the numerator. So when we look at that simplified numerator, x equals negative 1 is going to make that 0. And then there's a y-intercept when y is equal to negative 1/4. How did I find negative 1/4 as our y-intercept? Well, if we were to plug 0 in, we get 0 plus 1 over 0 minus 4, and that's just equal to negative 1 over 4. That's our y-intercept. You plug 0 in and evaluate it. Pretty simple. Okay, so let's plot each of these things on our graph, and then check it against Desmos to see how we did. All right, so I'm going to sketch those asymptotes first. Those are usually a good place to start. We have one at x equals 4. So here's my asymptote at x equals 4. We have a horizontal asymptote at y equals 1. So there's y equals 1 is my horizontal asymptote. I'm going to go ahead and plot the hole next. So our hole is at 1, negative 2/3. So we can plot that 1 and negative 2/3. It's about there. That's where our hole is. I'm going to sketch the x-intercept and the y-intercept. So our x-intercept at negative 1. So that's right here. When x is negative 1, y-intercept at negative 1/4. So that's like, it's easier actually if I use a mouse. That's like right here. Okay, so there's our y-intercept. And now let's go ahead and do some sign analysis. We can figure out what's the sign to the left and to the right of 4. So we're going to look just to the left and to the right of 4. So I'll do this in green. So I don't have a ton of space. Let's just, I'll try to make space. I'll make space at the bottom. So we're going to look to the left of 4 and to the right of 4. So if we plug in negative 3, not negative. I want just to the left. So 3.9, so we'll look at 3.9. Is this positive or is this negative? That's the question at hand. Well, the top is 3.9 plus 1. So that's a positive number. If I do 3.9 plus 1, I get something positive. It's 4.9. The denominator is 3.9 minus 4. Well, 3.9 minus 4, that's a negative number because 4 is more than 3.9. So you take away something more, you get a negative number. So we have a positive over a negative, and that overall is a negative. So I know for a fact that this is going down to negative infinity as I approach that asymptote from the left. 3.9 is just to the left of 4. And we can do the same thing if we were to look at something that's really close and on the other side, f of 4.1, for example. And we find the numerator is still positive because 4.1 plus 1, that's a positive answer. the denominator is now positive because 4.1, I plug that in, I do 4.1 minus 4, that's 0.1, that's positive. So we get positive over positive, and that's a positive result. So we know it's going up to infinity on the left side of that asymptote. And then it's going to just go towards the horizontal asymptotes like so. All right, let's go ahead and see how we did. Contacting the server for information. It needs to know where the link is going. Zoom down here. Okay, there's our graph. Let's see if I can look at them at the same time. We've got, yeah, that's not bad. Not bad at all. Okay, so we've got that hole, like I was saying, at 1, and, oops, 1, get there. Won't let me, there we go, 1, and it's undefined. It's about negative 2/3. That's what we said earlier. And then that y-intercept was at negative 1/4, and the x-intercept was at negative 1, so we've got those plotted correctly. It's going towards that horizontal asymptote at y equals 1. This is y equals 1. It's got that vertical asymptote at x equals 4, and it's going to negative infinity on the left and positive infinity on the right. And there we go. So we got that one graphed pretty nicely. Okay, let's do a last example, and we'll call it for this video. These take kind of a long time to go through because there's a lot of algebra there's a lot of things to check through. Okay, sketch the graph of the following rational function, 2x squared minus 3x plus 1 over x squared minus 2x minus 3. So again, we're going to factor and find the zeros. So factoring the numerator, 2x squared minus 3x plus 1, that actually factors nicely into 2x minus 1 and x minus 1. The denominator is going to factor and give us x minus 3 and x plus 1 as its factors. Okay, so we're just factoring these quadratics out. If you need a minute to work through this yourself, you can, but that would be the answer after factoring. So we can see from this there's no common factors, so there's no canceling. We're going to have no holes. We're going to have two x-intercepts, or two vertical, sorry, we will have two x-intercepts, but we have two vertical asymptotes, one at 3 and one at negative 1. So we have a vertical asymptote when x is negative 1 and one that's when x is 3. And that's these come from each of these. So yeah, that 0 and then that 0. There's a horizontal asymptote at y equals 2. That's the ratio of leading terms. 2x squared over x squared, that's 2. Simplifies down to 2. So we've got vertical asymptotes, 2 of them, and a horizontal asymptote at y equals 2. We've got two x-intercepts, 2 of them, because we have two numbers that make the numerator 0 and don't make the denominator 0. And those numbers are 1/2 and 1. Because that's, we have an x-intercept from this guy, we have an x-intercept from that guy. There's a y-intercept as well, and that's when y equals negative 1/3. Okay, how did I find that one? Well, f of 0 equals 0 minus 0 plus 1 over 0 minus 0 minus 3. And that's just going to be 1 over negative 3. This is negative 1/3. That's an easy one to find. You just plug 0 in. It's the constant over the constant at the end. So we're going to go ahead and start sketching each of these things on our graph. We're going to plot it all out. So the vertical asymptotes are going to be at x equals negative 1 and x equals 3. So let's sketch those in first. There's negative 1 and x equals 3. So 1, 2, 3. Okay, so we've got those vertical asymptotes. And now let's go ahead and sketch our horizontal asymptote, which is at y equals 2. Doing my best I can with this pen. So we've got these guys sketched. We're going to go ahead and plot the x-intercepts and the y-intercept. So those are our two x-intercepts, 1/2 and 1. They're really close together. The y-intercept is at negative 1/3. So those are all really kind of close together right there. A little bit hard to see. And then our next step is to do some sign analysis and figure out how is this going to work when we get close to each of these asymptotes. So what are the answers close to the asymptotes? So I'm going to go ahead and erase all this, and we'll do the sign analysis down here. Okay, so let's look at the left asymptote first. So -1. So we're going to plug in something really close to -1 but smaller. So that could be -1.1. Let's look at each factor and figure out, is this positive or is this negative? So we're going to look at 2x minus 1. Is that positive or is that negative? Well, we have -2 times -1 minus 1. That's going to be a negative answer. The first factor is negative. -1.1 minus 1, that's also negative. So that's a negative answer as well. Then we look at the denominator factors. -1.1 minus 3, that's a negative answer. -1.1 plus 1, that's a negative answer. So we have negative, 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 negative. There's 4 negative signs, so the result overall is positive. So what that tells us is to the left of -1, this is to the left of -1, just to the left, it's a positive answer. I totally biffed that. There we go. Totally biffed. It's up here. It's going up to positive infinity to the left of -1. And we'll do the same thing on the right side of -1, the same thing on the left side of 3, and on the right side of 3. So let's look at something that's just to the right of -1. So we're going to look at f of -0.9. And the numerator is staying negative, negative, and the denominator is negative, and then now this one switches because -0.9 plus 1 is now a positive number because 1 is more than -0.9. And so we have 3 negative signs, and so that's overall negative. So we found now it's going down to negative infinity as we're to the right, just to the right of -1. So we can look again on either side of 3. So we're going to look at 3. Okay, let me go ahead and erase this. So f of -2.9, we're just to the left of 3 now. So we have 2.9 times 2 minus 1. So that's definitely a positive answer. We have positive. 2.9 minus 1, that's definitely a positive answer because that's 1.9. 2.9 minus 3, that is a negative answer. That's negative because 2.9 minus 3 is a little bit negative. 2.9 plus 1, that's a positive. So we have 3 positives and 1 negative, so that's overall a negative answer when you multiply those all together. So to the left, we're negative as well. We can start connecting the graph a little bit. So we connect, we've got those 2 zeros, something like that. And then we'll look on the right side of 3. So we're going to do f of 3.1. And we have positive on top when we plug those in. And we have a positive now and a positive, and everything is positive, so the result is positive. So we're over going up to positive infinity to the left, or to the right of 3. Okay? And so our graph is going to do something like this. We're going to zoom in towards those asymptotes as we go off to the right and off to the left. And we've got that kind of funky U in the middle. So let's go ahead and compare this with Desmos to see how well we did. Okay, so here's our Desmos graph, and we can see those two x-intercepts are right there at 1 and 0.5. They're really close together. That y-intercept is right there at -1/3, as we said. So they're all kind of smushed together right there. And we have this U, upside down U in the middle. So it's going down to negative infinity and down to negative infinity as we get close to each of those asymptotes in the middle. And then the other asymptotes are doing what we kind of expected them to do. For this one, it's going up to positive infinity here. This one, it's going up to positive infinity there. And we've got that end behavior doing what we expected to do, going towards 2 to the left and 2 to the right. All right, that wraps up what I wanted to show you guys in this video, and I'll see you guys in class tomorrow.